So the topic of today's video will be Laurent series, and we will see that to find a Laurent series we need a singularity, and that should be a special type of singularity, isolated singularity. I will define what is an isolated singularity, right? And let's recall what we did in our last video. We expanded a function, analytic function, in positive powers of z minus z naught, and that was called Taylor's series, right? And that was only possible due to the fact that the series was centered at some point which was analytic inside some domain, right? But this time fz will be a function which is not analytic at some point. Let that point be z naught, and we'll search a series centered at z equal to z naught, means centered at that singularity, right? So this time we'll be having positive as well as negative powers of z minus z naught, right? So I will start with the singularity. I will recall the definition of singularity. What is a singularity? A point z equal to z naught is called a singularity of a function fz if fz fails to be analytic at that point, right? Suppose you have function 1 over z, right? And clearly the denominator goes to 0 if you put z equal to 0. So we can say that z equal to 0 is a singularity of function 1 over z, right? And there are so many functions having two or more singularities, right? So I will start with the isolated singularity. Means there are two types of singularities. One is the isolated singularity and the other one is non-isolated singularity, right? So as the name suggests that the isolated singularity is a singularity in which its neighborhood does not contain any other singularity, right? Suppose you consider a function f z equal to 1 over z, right? In any domain, or in domain unit disk mod z less than 1, centered at 0 and radius equal to 1, right? And you have function f z equal to 1 over z. Clearly z equal to 0 is a singularity of this function, and this singularity is isolated singularity because there is no other singularity other than z equal to 0 inside the unit disk, right? So we will be using this idea in order to get this Laurent series, right? The basic condition for having this Laurent series is that the singularities should be isolated in nature, right? So I will give two examples. One, a supporting example of isolated singularity, and the other is a non-example of isolated singularity, and we'll see that in two examples, right? So to understand what is an isolated singularity, right? Rather than giving its definition, I would take a simpler example, right? Okay, fz equal to 1 over z minus 1, right, is not analytic at z equal to 0 and z equal to 1, right? And suppose I take domain in domain mod z less than 1, right? So except at these 2 points the function is analytic, we can say that. Okay, then let me draw the diagram of this situation. This is my mod z less than 1 is an open disk centered at origin and radius equal to 1. So we'll draw an open disk like this. You can see that the disk is centered at origin, right, and its radius equal to 1, and the singularities are z equal to 0 and z equal to 1. Let me put a cross there. This is z equal to 0 and this is z equal to 1, or should I take it z equal to 2? Let me take it z equal to mod z less than 2, right? Fine. Then this radius will be equal to 2, right? So this is the first singularity, z equal to 0, and the other singularity will be here, z equal to 1, right? This is z equal to 0, this is z equal to 1, right? Okay. Obviously these two singularities are isolated singularities, and why we are calling them isolated? Because if you draw a small neighborhood, right, I will draw that neighborhood with a different color. This is z equal to 0, right? Taking z equal to 0 as a center, you draw a small neighborhood. Small neighborhood means a small open disk, right, this way, and let me put dots everywhere, right? So it looks like an open disk centered at z equal to 0, right? And you can see that you focus on this red colored disk, open disk, you see that this disk contains only one singularity, and that is only z equal to 0, which is the center of this disk, right? It means that z equal to 0 is an isolated singularity. Had we drawn a disk taking z equal to 1 as center, if I draw another disk, a small disk, right, this way, and then you can see that there are so many points in this disk centered at z equal to 1, and there is no singularity in this disk other than z equal to 1. It means that z equal to 1 is also an isolated singularity, right? So the point is that you should be able to draw a disk as small as possible, right? So that it does not enclose any other singularity other than the center of the disk, right? So this is a disk, two disk, and this is the only singularity. First disk, z equal to 0 is the only singularity enclosed in disk, z equal to 1 is the only singularity enclosed in second disk. So both of these singularities are isolated singularities, right? So I will write that here, z equal to 0 and z equal to 1 are isolated singularities, and the reason is now known to you. You know why we are saying that, right? Now this is a supporting example of isolated singularity. Now I will take a non-example, right? And the non-example is a non-example, right? And this is an example, right? Fine. Non-example is this: if fz equal to log z, right, has a singularity, right, at z equal to 0. This function has singularity at z equal to 0. If you convert this in polar form, right, and then apply CR equations, then they will hold everywhere except origin, right? We have done this example in our previous videos, right? So it is a singularity at z equal to 0, right? And one more thing, this function log z is not defined for the negative real axis, or you can say that non-positive real axis, right? That is called the branch cut of log z, right? In order to restrict this function to a single valued function. Actually, log z is a multi-valued function, and why we are calling it as multi-valued? Because if you put z equal to r times e to the power iota theta to convert this function into polar form, then you will get log r plus log of e to the power iota theta, right? And ultimately we will be having log r plus iota theta, right? And due to that theta factor, right, the function becomes multi-valued. Why? Because you take any point on complex plane, right? You take any point on complex plane, and that point is completely described by the values of r and theta. Means whatever is the its distance from the origin, that is called small r, and whatever is the angle that radial vector makes with the positive axis, that is called theta, right? And due to this theta, this function becomes multi-valued, right? And why it becomes multi-valued? Because I should write it here as f. If I put r, z equal to r e to the power iota theta, then it will become log r plus iota theta. That's simple. Due to this theta, right, it becomes multi-valued function. Why? Because taking any point on complex plane, it will have, suppose you have point z naught on a complex plane, and it has an angle of 30 degree with the positive direction of x-axis, or you should say theta equal to 0. Then it will also make an angle of 360 degree plus 30 degree, right? That will be 390 degrees, because you can complete a full circle, right, and come back again to that point. Then the angle will be plus 2 pi, means 2 pi will be added to that angle, right? What do I mean? That if this is a point, suppose this is a point, let this point be z naught, and it is making an angle of theta degree with this theta equal to 0, and this is obviously theta equal to pi by 2, and so on, and this angle is theta, right? Then this point will be represented, and this distance is r, then you will represent this point by r comma theta, p r comma theta, right? Moreover, this point can also be represented by p r comma 2 pi plus theta, right? And you should understand why I have written 2 pi here, because you can come back to this point by tracing a full circle, right? And in that case 2 pi will be added, right? And moreover, you can take two complete circles, in that case p r comma 4 pi plus theta, right? So due to this theta factor here, this function becomes multi-valued, right? So what do we want? We want we want that this function becomes single valued, right? And in order to restrict this function to a single valued function, we should not cross this axis, this one negative part of axis, right? In that case, this function will be restricted to a single valued function, right? Or we can say that we cannot increase our angle beyond this 2 pi, right? So that's why this function fz, right? When we write this function fz like this, we write here such that this theta must lie between 0 to 2 pi, right? Means this axis, this negative x-axis is deleted, right? Okay. So we can say that this function log z has singularity at z equal to 0, right? And plus all points lying on these non-positive real axes are also the singular points of this log z, right? In order to restrict it to a single valued function, right? Let me draw that figure for this log z, domain of log z where it is analytic, right? Okay. So the picture will look like this. Means this is deleted, this is deleted, and this axis is here, right? Now I will draw the domain of convergence of this function log z, right, with my red colored marker. And the domain looks like this. It will extend up to infinity, so I am drawing it up to here, up to this height only. In this picture, we have deleted this origin and we have deleted this non-positive axis, or you can say negative axis union 0. So that part will be, that deleted part will be called as non-positive axis, right? So I will write the domain D here. Domain of convergence, domain of convergence of log z is the whole complex plane, right? Whole complex plane C, and the non-positive axis subtracted from it. So I will put negative sign minus this set. Nature x comma 0 because y is 0 everywhere, right? And x is less than or equal to 0, right? So this obviously indicates the non-positive axis, right? Because y is 0 everywhere. You can see that on this axis y is 0 together with this point also, right? And x is negative or 0, right? So it completely indicates the domain of convergence of the function log z, right? Now we'll talk about the isolated or non-isolated singularity. Isolated singularity is clear from this example. Now what is non-isolated singularity? Actually z equal to 0 is a singularity of this function. It is very clear, right? Now I will draw a disk around that z equal to 0, right? And we'll see that what happens inside that disk, whether there are other singularities other than z equal to 0, or there is only one singularity z equal to 0. So I should draw that disk with my black marker this time because the domain is already red colored. So this will be my an open disk centered at z equal to 0 because z equal to 0 is singularity, right? And it has very small radius. Let the radius be epsilon, right? Okay. You can see that there are, this is z equal to 0 is the singularity which is obviously the center of this disk, and there are other singularities also. You can see that at this point is the point on a negative x-axis. This singularity is also enclosed in this disk. Moreover, there are so many other singularities on this negative part of x-axis which also belong to this disk, right? No matter what is the size of your disk, how small you draw that disk, there will be at least one or more singularities other than z equal to 0 inside your disk. You can see that from the picture, right? You cannot say that z equal to 0 is the only singularity lying inside this disk. There will always be other singularities other than the center of the disk which will belong to this disk, and hence we will say that z equal to 0 is non-isolated singularity, right? So I will write here, writing that, right? Because for any disk as small as possible, right, there will be always other singularities other than z equal to 0 which will belong to the disk, right? So you should clearly understand the difference between the isolated singularity and the non-isolated singularity, right? And now we'll come to our main topic, that is Laurent series. Okay, so Laurent series, in order to write a Laurent series, that is a special kind of power series with the negative powers of z minus z naught also. We need that center of the series should be an isolated singularity, right? If we want an expansion, right, centered at the series centered at non-isolated singularity, right, then that is not possible. Series is not possible, right? So I will start with a small example first, and then I will write the Lorentz theorem, right? So what is the Laurent series? It is a special kind of series. It is a special kind of series, right, having positive, or should I say non-positive, or not positive and non-positive, okay, fine, or negative, we emphasize on negative and non-negative powers of z minus z naught, right, where z naught is an isolated singularity, right? So this is the important part. The center of the series must be an isolated singularity, right? Okay, so the series is of this nature, that is fz. We have a series of this form, or shouldn't I write fz? I should write series only. The series is of this form: summation a minus k z minus z naught to the power minus k. These are the negative powers of z minus z naught, and we start with k equal to 1 to infinity, and then positive powers also, k equal to 0 to infinity, a k z minus z naught to the power k, right? So you can see that this part will contribute to the negative powers of z minus z naught, and this part will contribute to the non-negative power of z minus z naught. Why we are calling it non-negative? Because there will be a constant term also, a naught, and this will be 1, right? So constant term will be treated as non-negative powers of z minus z naught, right? Okay, so this is the idea. For example, I should start with a small example. Let me if a function is fz equal to sin z over z cube, right? You can see that this function, and this function has singularity at z equal to 0, right? Fz equal is this has an isolated singularity at z equal to 0. And why we are calling that z equal to 0 an isolated singularity of this one? You can see that z equal to 0 is a singularity. You should verify it. If you put z equal to 0, you will get 0 by 0 form at first. Then you will apply LH rule. It will become, on applying LH rule, it will become cos z, and it will become 3z square. And then you put z equal to 0, then it will become 1 upon 0 form, right? It means that it is an, obviously z equal to 0 is a singularity of this function. And why we are calling it isolated singularity? Because there is no other singularity, only z equal to 0 is a singularity, right? And if you draw an open disk or open or neighborhood around that z equal to 0, there will be no other singularity other than this one, z equal to 0, right? So that's why we are calling it an isolated singularity, right? So it means that Lorentz series is possible, because this is the important assumption of getting Lorentz series, having isolated singularity at that point, right? Okay, so what we'll do, in order to get a Lorentz series, we just rely on geometric series, right? Means the well-known expansions of exponential function, sine function, cos function, and you can see that here we have this well-known sine function, and you should remember the series of sine z, right? Then fz equal to 1 over z cube, and expanding this sin z by its usual expansion, that is z minus z cube over 3 factorial and plus z to the power 5 over 5 factorial minus z to the power 7 over 7 factorial and so on, right? Now taking this 1 by z cube inside, we will get 1 over z square minus 1 over 3 factorial plus z square over 5 factorial and so on minus z to the power 4 over upon 7 factorial, so on, right? And you can see that this is obviously a Laurent series. Why? Because it is containing negative powers of z. You can see that, right? So this term corresponds to this one, right? And all these positive powers and constant term, this one is for this series, positive powered series, and they have special names. And this is called, this part is called actually, this is called analytic part, right? Right, and this is called principal part, right? So the positive powers in, or you can say the non-negative powers, this part is called analytic part and this is principal part, right? So similar to this one, this is your principal part and this is your analytic part, right? Fine. And yes, we have to talk about the convergence of this whole series, right? When this whole series converge, this series converge in some annular region, right? Means a kind of ring, right? Okay, I will write that here, which will, I should write that here, isolated singularity, okay, principal part, analytic part, okay, let me call it first converges for annular region, and that region should is R mod z minus z naught less than capital R, right? You can see that the series is centered at 0, right? Means your annular region, a concentric, the region between concentric circles, right? That both of those circles are centered at z naught, and the inner radius is small r and the outer radius is capital R, right? This is the domain of convergence of this type of series, first one, right? Similarly, we can write the domain of convergence for this one, right? You can see that for this principal part, this is not analytic at z equal to 0, right? But analytic everywhere, and this is also analytic everywhere. Means you have to exclude z equal to 0, right? So the domain of convergence will be converges for 0 less than mod z less than infinity, because 0 is the only number, only singularity of this series, right? So we can write the domain of convergence this way, right? Now I will write Laurent's theorem, statement of Laurent's theorem. Laurent's theorem, right? So what does it say, Laurent's theorem? It says that if fz has an isolated singularity at z equal to z naught, right? Then fz can be expressed in a power series, a special power series, right? Can be expressed in a, I shouldn't write power series, right? In a series containing negative and non-negative powers of z minus z naught, that is this way. Fz, the function fz is expanded in this way, right? Or should we write them collectively? If I write here ak is z minus z naught to the power k, and I should start from it from minus infinity to plus infinity, right? So on adding them, you can write it in this way, right? So this is a similar representation for this one. You can write a 1 also here, that is fine. Which converges in the annular region R less than mod of z minus z naught less than capital R, right? Okay, and one more thing, this coefficient where ak equal to 1 over 2 pi iota closed line integral along curve C f of z over z minus z naught to the power n plus 1 dz, right? C is a closed curve, simple closed simple curve inside this region R less than mod z minus z naught less than R, right? And you know about z naught. Z naught is the singularity, right? So I will draw the curve C and domain D, right? Okay. Or should I write it inside capital D? Inside domain D, right? So first we'll draw the domain D as we have been doing in our last videos. First we should draw the domain of convergence, the whole domain D, right? And this time Z naught is a singularity, right? So I will draw a domain with holes, one hole only, right? So this is a domain of arbitrary shape, and this is a hole. And why we are making a hole here? Because at this point you have Z naught, right? And this is your center Z naught, right? And you can see that taking this smaller radius, small r, this is a small r, right? And you have this circle, this is circle, right? And then big circle, capital R, right? This is capital R. And here is my curve C. This is my curve C of like this one. This is C, closed curve C, right? So you can see that this center is Z naught. The inner radius is small r, right? This one. And the outer radius for the outer disk is capital R. And we can say that the series converges for this region, means the annular region between these two black circles, right? This portion, ring shaped portion between the smaller and the bigger circles, right? So this AK is given by this formula, right? And you can see that this FZ is given, already given. C is this curve, right? And C is a closed curve, simple curve lying inside domain D. This is a domain D, outer red one, domain D, right? However, in practical, you do not need this formula. This is not required, right? In order to get a Laurent series, we will not use this formula, right? We'll just rely on geometric series, like as I did in this example, right? Just expand by using geometric series. Okay. So we'll take examples of Laurent series, right? And the proof of this Laurent theorem again use Cauchy integral formula and Cauchy's inequality ML inequality and so on, right? So the proof is quite complicated. We'll do numericals of it, right? So example number 1, expand fz equal to 1 over z minus 1, z minus 2 in the region, and the first part is you can see that the singularities are 1 and 2, right? And if I take center as 0, then that should be less than 1, and here I should write 0 is allowed. Okay, fine. Okay, and second is mod z greater than 3, right? And third should be, if I take center at 1, mod z minus 1 is the center, then 1 is the center, then it should be greater than 0 and less than 1. Fine. Okay, and fourth part is also possible, d part d. If I take 0, yeah, 0 as center, then 1 to 2. Okay, 1 less than mod z less than 2, right? So these are the 4 possible domain of convergence of this function, and let me start with the first one, solution. So in order to get a Taylor's, Lorentz expansion that will contain obviously positive and negative powers of z this time, z minus 1 or z minus 2, we should first express this function in partial fractions, right? Fz should be written using partial fraction, and if I write it using partial fraction, then I will get z minus 2 should be here, minus z minus 1, then it will become 1, 1. Yes. So this is the partial fraction representation of this function. Okay. Now let me call it equation number 1, right? And focusing on first part here, mod z less than 1, right? It means that you need an expansion in powers of z. Why only powers of z? Because you see that this is only z, means the series will be centered at origin, right? Okay, I will draw the domain also. So mod z less than 1 means this. This is an open disk centered at origin. You can see that this origin is the center and radius is equal to 1, right? And you can see that the function has singularities at 1 and 2. This is a singularity 1, and here we'll have 2, right? X-axis and y-axis. So obviously your disk is not passing through 1 because this disk has no boundary, right? The assumption is also that the function should be analytic in that region, right? And you can see that inside this red region, this function is analytic because the disk is actually not passing through 1. 1 is the singularity of this function. So 1 is at the boundary, and the boundary is not included for this disk because this is only less than symbol, means the boundary is excluded, right? So okay, this is my fz, right? Okay, now fz equal to 1 over z minus 2, this is z minus 2, and you need an expansion in powers of z, right? So you should take common minus 2 here, minus 2 should be taken common, and inside we'll have 1 minus z by 2, right? And this step is very important, very crucial step, right? Why it is crucial? Because there are 2 possibilities, either you will take minus 2 common or z common, right, in order to get a factor of the form 1 minus x or 1 minus alpha, right? Okay. So you have to create a 1, and this 1 can be created in 2 ways. Either you take minus 2 common as I have taken, or you can take z common, right? So 2 possibilities are open at this stage. But focus on this thing, right? You want a geometric series that should converge inside some domain, and that is only possible if this alpha, this is alpha 1 minus alpha, the mod of this alpha should be less than 1, right? And you can see that since mod of z is less than 1, modulus of z is less than 1, it implies that mod of z by 2 will be less than 1, and that's why this expansion is the only possibility at this point, or taking out minus 2 common is the only possibility, because at this whatever you are getting at this point 1 minus whatever alpha, its modulus should be less than 1, right? And since we are saying that mod z is less than 1, then mod z by 2 will be automatically less than 1, right? So I will write that in detail. 1 minus z by 2, and the reason for this thing, I am writing the reason here, as mod z less than 1 implies mod of z by 2 will be automatically less than 1, and in order to expand it using that geometric series, right, that is valid if and only if this condition hold, right? Means the modulus of this number should be less than 1, right? So be careful at this point. And now this one, what should be taken common? Should I take z common or 1 common, right? There is no need to take common. You should write it 1 minus z, and this sign will become plus 1 over 1 minus z. But again you check that for this alpha, right? I will write it here for this here. For this alpha, obviously its modulus is less than 1. It is given in the question, right? Now I can expand these two. I will take this factor in the numerator, and then I will apply the formula of 1 minus alpha to the power minus 1. Then it will become 1 plus alpha square, right? And so on. And for this 1 plus z square and so on. So this is the answer, right? And if you want to write it in that fashion, this way, means negative part and the non-negative part, so you should take the negative powers of z. Where is the negative powers of z? There is no negative powers of z actually, right? Because this is not an annular region, this is a disk, right? Simply connected disk, right? So this is actually a Taylor series, right? And why we are getting a Taylor series? Because this disk was not enclosing any singularity, right? Or you can say that this is a simply connected domain. It is not a annular region, right? In this case, C and D, you will get negative powers also, right? Okay, so I will take 1 minus 1 by 2, that will be 1 by 2, okay, and the z minus z by 4, that will be 3z by 4, I think, right? And this is minus of 1 by 8 and plus 1 minus 1 by 8, that will be 7 by 8, 7 by 8 z square and so on. So we can see that no negative powers of z, right? It implies that this is actually Taylor series, which is a Taylor series, right? It indicates that this function is actually analytic inside this disk, right? Taking its second part, B part. B part, and here we have this one here, mod z is greater than 3, right? It means that the disk will be centered at 0 because this is z minus 0, and the radius will be greater than 3, means it is actually outside of disk, right? Radius 3 and center 0. So this is I will draw that with red marker actually. So this is a z equal to 3 point, right? 3 is yeah, greater than 3. Oh, should I write it at mod z? Singularity is at 2, right? So I should write it as 2, mod z greater than 2. 2, fine. So 1 is the singularity, z equal to 1 is a singularity, 2 is also a singularity, right? You can see that from function, and our disk is centered at 0, but outside of this one. Means the domain will be like this one. since we have this greater sign here, means the domain of convergence is the outside of this disk actually, not inside, right? And you should extend this red colored region up to infinity on all sides, right? Okay, so this is the domain of convergence, the outside of this disk. Okay, now this is my equation number 1. Therefore, fz equal to, you can see z minus 2, right? So now again comes the decisive step. Should we take z common or 2 common, right? I think 2 by z is less than 1, so I should create 2 by z here. I should take z common, so it will become z common, right? And it will become 1 minus 2 by z. But important point is that this alpha, this number is actually less than 1. You can see it from here, as mod z greater than 2, it implies that 2 by z mod less than 1, right? And that's what we need here. This alpha should be less than 1, right? And for this one, plus, write it as 1 minus z, or z should be taken common. I think z should be taken common, minus 1 over z, and we'll have 1 minus 1 by z. And why we have taken z common? The reason is this one, as mod z is greater than 2, right? Means the number is greater than 2, positive number, it's modulus. It implies that it should be greater than 1 also, right? Something is greater than 2, that should be greater than 1 also, right? And it implies that if we take this mod z here, 1 over z less than 1, right? And that's why we have created 1 by z here at this point, right? Okay. Now it is all about expanding 1 by z, and if you take this in the numerator, then the expansion will give you 1 plus 2 by z plus 2 square by z square, and so on. And for this one, minus 1 by z, 1 plus 1 by z plus 1 over z square, and so on, right? And you can see that, yeah, all powers are negative powers, right? 1 by z minus 1 by z, that will be cancelled, 2 over z square, and this is minus 1 over z square, then it will become 1 over z square, then 4 upon z cube, and minus 1 upon z cube, that will become 3 over z cube, and so on, right? So all powers of z are negative, right? Okay. Third, and again, this is a kind of annular region. However, this was not annular region, this is a disk, right? Open disk, but this is not a disk. Actually, it is an annular region, right? And if I say it is an annular region, there should be small r and capital R. See this? Annular region indicates the small radius and bigger radius. The small radius is actually 2, right? And the bigger radius is infinity, because this region is extending up to infinity. So it can be written as this way also: 2 less than mod z less than infinity. So this is actually another representation of this annular region, right? So it, small r is 2 and capital R is infinity, right? That's why we have got negative powers of z, right? For any annular region, you will always get some negative powers of z. Okay. Third part, C part, that is here, 0 less than mod of z minus 1 and less than 1, right? Okay. So drawing the picture first, the singularities are at 1 and 2. So this is a 1 and this is a 2, they are singularities, right? And you can see that the center of this annular region is 1, means this is the center, right? And the radius is also 1, right? So what does it mean? It means that it will be like this, means this is excluded, obviously. This one is excluded. You have a hole at this point. And why I'm saying that you have a hole at this point? Because I will remove this dot from here, because actually this mod of z minus 1 is not equal to 0. It is clear that is greater than 0, and you can get z minus 1 equal to 0 if and only if you put z equal to 1, right? It indicates that you cannot put z equal to 1 here, because if you put z equal to 1 you will get 0, and 0 is not the value which is taken by this z minus 1, right? It means that z equal to 1 is not allowed, right? So you will make a z whole at z equal to 1. Okay, and you see the radius is equal to 1, so you should draw a disk. You can say that this is small r is equal to 0, capital R equal to 1, and the center should be 1. So I have taken center at 1, the radius is 0, greater than 0, let it be 0.00001, right? So that circle is visible. This radius is 0.00001 or epsilon, right? And the bigger radius should be equal to 1, so the bigger circle will be like this one. Pass from here, right? Oh, it should move from here. Radius 1, like this. Okay, so we'll color it by red. This is the annular region, a ring region. Right. Now, therefore, fz equal to, where is your function? 1 over z minus 2, 1 over z minus 2 minus 1 over z minus 1, right? Now you have actually two circles this time, so be careful at this point. So take a decision whether I should take common z or 2, right? I think if I take, I should create z minus 1 everywhere, because the series will be containing powers of z minus 1, and that is again important point. I should write it this way, z minus 1 minus 1, right, in order to achieve a series of powers z minus 1, and this is fine, z minus 1, I will leave it as it is, right? Now, either I should take z minus 1 common or 1 common. If I take 1 common, that will be 1 minus z minus 1, and this is less than 1, yes, fine. This is fine, z minus 1. No need to take common from this second term, because you need z minus 1, and z minus 1 is here, so leave it intact, right? Okay, and the reason for this one is that since modulus of this alpha is less than 1, you can see from here this portion, right? Okay, from here, and this is fine. Now I will expand this. On expanding, I will get negative sign, and then 1 plus z minus 1 plus z minus 1 whole square, and so on, and this is 1 over z minus 1, right? And ultimately I will get the only negative power of z minus 1 is this term, so I will write it here, z minus 1, and all terms minus 1 minus z minus 1 minus z minus 1 whole square, and so on, right? So this is your principal part, this one, and the rest of the series is your analytic part, right? Okay, and you can see that the negative powers of z minus 1 are appearing here. Why? Because again this was an annular region, right? Okay, so last part, D part, D here, 1 less than mod z less than 2, right? So this is a 1, and the other singularity is 2, and you can see that the circle is centered at origin. This is mod z only, right? And the inner radius is smaller one, and small one, and sorry, inner radius small r is 1, and the capital radius capital R, bigger radius capital R is equal to 2, right? So it will be concentric, two concentric circles like this one, z equal to 1, outside of this z equal to 1, and inside of 2, you can think like that also, right? Mod z greater than 1 means outside of unit circle, and mod z less than 2 means inside of circle of radius 2, right? So this is your region of interest. This point is 1 and this point is 2, right? So the red colored region will be where the function, the series converge, is this region, the annular region, right? Okay. Therefore, fz equal to first is 1 over z minus 2 and the second is 1 over z minus 1, taking that equation number 1, right? And now you should decide what should be taken common, either z or minus 2. I think since z by 2 is less than 1, so we should take minus 2 common from here. If you take minus 2 common, then you will get 1 minus z by 2. And why this step is valid? Because this alpha, mod of this as mod of z is less than 2, you can see from here, mod z less than 2 implies mod of z by 2 is less than 1. That's why we have created z by 2 here. And 1 is greater than z, so 1 by z should be created. So z should be taken common, 1 minus 1 by z. And the validity of this step lies in the fact that 1 less than mod z implies that 1 by z modulus less than 1, and that's why I have created 1 by z here, right? This is very important step. Okay, and after this step you should expand it. That will be 1 plus z by 2 plus z square by 2 square and so on, and minus 1 by z, 1 plus 1 by z plus 1 over z square and so on, right? And you can see that there are negative powers of z also and non-negative powers of z, right? Okay, so I think that's fine, they cannot be added, right? Fine, this is a constant term, okay, and this is your non-negative part, the analytic part, right? And this is your principal part, right? Okay, so this is a series expansion in all cases, one function but different domains, right? And you can see that whenever you have this annular domain, like in B, C and D, this is also an annular region, right? Means the small radius is 2 and the bigger radius is infinity. So in the last three cases, B, C and D, we got series with some negative, some or more negative powers of z, right? But in the first case, since it was not an annular region, that's why we got Taylor series, all positive powers of z, right? Taking another example. Example number 2, expand fz equal to 1 minus cos z over z cube, right? About z equal to 0, right? So we are asked to expand this function about z equal to 0. So let me check first that whether z equal to 0 is a singular point of this function or it is analytic at z equal to 0, because that is also a decisive step. If at some point the function is analytic, then you will obtain Taylor series, right? And for that you have to refer to our last video. And if the function is not analytic at that point, and that point should be isolated singularity, the other point is that, then you will obtain a Lorentz expansion, right? So first you should check by putting this z equal to 0 here, or limiting value of z equal to 0, that is 0 by 0 form. You can see that you are getting 0 by 0 form, right? But what happens if I apply LH rule here? Then the differentiation will be sin z and 3z square, and again you will get 0 by 0 form. But if you apply LH rule second time, then you will get cos z over 6z, I think. And in that case you will get 1 over 0, and it indicates that you are getting infinity actually for limiting value of z tending to 0. That's why it is a singularity. And since there is no other singularity for this function, right, so it will be called as an isolated singularity, right? Solution, I am writing that directly, you should check it clearly. Z equal to 0 is an isolated singularity of fz. Verify it by yourself, right? Verify. Okay, so we'll get a Laurent series, and to get that series, what we'll do, we'll just use the series for cos z, right? We already know the series for cos z, that is 1 minus z square by 2 factorial plus z to the power 4 factorial and so on, right? And ultimately we'll get, I think I should write one more term also, z to the power 6 by 6 factorial plus dash dash. Then 1 and 1 will be cancelled out, and then plus z square by 2 factorial, then z cube, that will give me 1 over 2z, I think, yeah, minus z over 4 factorial, and then plus z cube over 6 factorial and so on, right? So you can see that there is a negative power of z as well as positive power of z, so hence it is a Laurent series, and obviously it has to be. And what if we try to write the domain of convergence, or that annular region? Since we are getting a Laurent series, negative as well as positive powers of z, so we should write the domain of convergence in annular form, right? Which converges for you can see that all series is in powers of z, right? Means the center of the series is 0, right? And since z equal to 0 is not allowed, you can see from here or here also, so 0 less than, and since you can see that this function is analytic everywhere except at z equal to 0, so the bigger radius will be infinite, right? So this is a domain of convergence for this, right, example. Okay, I will take one more example. Expand fz equal to 1 over z plus 1 0 minus 1 inside an annular region as small as possible, right? Fine. So this time the region is not given, but you can see that the singularities are at z equal to 0 and z equal to minus 1 are singularities, right? And if you draw those singularities, this is z equal to 0 and this is z equal to minus 1, right? Minus 1, and you want that a series inside some annular region, right? Actually there are 4 possibilities, right? When you get 2 singularities, then there will be 4 possible regions inside which this series converge, right? As we did in first example. Now you want that region, annular region, as small as possible, right? So if you take the center of the series at z equal to 0, right, then there will be hole here obviously because it's a singularity, and the radius of the circle will be up to 1, and in that case that will be radius will be almost equal to 1, right? Okay, fine. So let me take this inner radius greater than 0, right? Not equal to 0, greater than 0, and the outer radius is 1. You cannot extend your circle, the outer circle, beyond minus 1. In that case it will enclose a singularity, right? So be careful at this point. And this minus 1 is actually lying on the boundary of the disk, and since our disk is an open disk without boundary, so there is no danger, right? And you can see that this center has been removed, means actually there are 2 circles. One is the smallest circle of radius, very small radius, greater than 0, and this is of radius 1, right? So this will be my region, and I will shade it with my red marker. This is my annular region where the series will converge, right? And for this you can write as 0 less than, because the smaller radius is 0, greater than 0, mod z centered at 0 and up to 1, right? You can see that the radius is equal to 1. So singularities, so the domain will be 0 mod z less than 1, right? Now I will write my series using partial fractions. Should I write it this way, z here and minus 1 over z plus 1? You can see that on taking LCM you will get this, right? And now since the center is 0, you can see it from here, center is 0, so leave this term intact. Don't try to take anything common, because we have z here also, right? And if I write it as 1 plus z, then it will be fine. Do not take out common, or you can take 1 common, that is fine, or you should take z common, but that will be wrong, because in that case here you will have, if you take z common, this term will become 1 over z, right? And 1 over z should be less than 1, means that z should be greater than 1, and here you can see that mod z is less than 1. So you cannot take common, or you can take 1 common only, right? This will be 1 by z minus 1 plus z to the power minus 1, right? And I will write y here, the reason, right, to write in this way, 1 by z minus 1 minus z plus z square minus z cube and so on. I think all terms are minus, no, minus plus are fine. So this is the answer. This is the negative part, principal part, and this is the analytic part, right? And this series is valid for this domain, right? So this is it for Laurent series, and you have seen that Laurent series, you can obtain a Laurent series whenever you have a domain of convergence which looks like an annular region, right? Otherwise you will get the Taylor series, right? Yeah. So that's it for this video. Thanks.